I'm really pleased to welcome to the stage Sonny Bailey, who's going to talk to us about iceberg detection.
Hi everyone, thank you for having me. I am a postdoc in iceberg detection at Lancaster University, so I've travelled quite a long way for this one. So it's great to see everyone. I haven't been doing neural networks for so long, but I've been doing a lot of work on iceberg detection for ever since I started my PhD. So a little bit of background context I'm going to give you guys. So climate change obviously means icebergs are breaking off of these ice tongues and ice shelves. About 30 to 40,000 icebergs break every year, and the problem with this is, of course, the Arctic has a lot of shipping operations going on. That cost about $10 billion a year. When we have iceberg ship collisions and incidents, despite that modern radar technology, we have a lot of insurance claims. We have a lot of carbon emissions and the goal really for iceberg detection in this context is to kind of make that a little better for everybody. So there was a new approach to detection that is being considered here that utilizes deep learning. Icebergs are of course major hazards to ocean operations, not just ships but oil rigs, and they can also be problematic for if you're in indigenous areas of Canada and you are fishing. Your fishing supplies could be disrupted by icebergs in the air. I'm just going to give you a little brief introduction to what icebergs actually are. Pieces of freshwater ice broken from a glacier. In the Arctic you've got glacier tongues. In the Antarctic you've got ice shelves. They can drift into open water quite easily, or they become embedded within sea ice flows. Now an important aspect about my work in iceberg detection using radar images is that icebergs and sea ice have a very similar backscatter signature, and that causes problems when it comes to trying to identify them. And again, that's one reason we're using this deep learning approach. They can also be classified by size and by shape. And the second problem that we have is that smaller icebergs are harder to detect. And as you'll see in a minute, we use a Sentinel-1, a synthetic aperture radar, which only has about 90 meters spatial resolution. So icebergs that are around 100 meters in length or smaller are very hard to actually detect. Iceberg detection has been an important field for a while. The importance has been raised even further by Titanic sinking in 1912. A little fun game for you. If you are interested in understanding how icebergs float or how icebergs topple over as well, you can go to this link here and it will tell you how to do that. You can draw an iceberg any shape you want, and it will do it all for you. But really only about 11% of the iceberg is visible above the ocean surface, and that's where we get the term tip of the iceberg from as well. So yeah, aside from that, the idea that we're using actually came from what my boss does, which is astrophysical galaxy cluster detection, using an object detection method shown here. Well, I'm not going to go into that, I'm not an expert, but the same idea applies. Okay, so a little bit about the that we're using. We are using synthetic aperture radar. Actually, I'm using a technique called polarimetric synthetic aperture radar, SAR. And what that means is we take, basically take Sentinel-1 images that are dual pole, and by dual pole we mean we're using two different polarization channels. We're specifically using a co-pole channel and a cross-pole channel. A cross-pole channel is horizontal, vertical, and a co-pole is horizontal, horizontal, vertical, vertical, etc. But we're also validating this using Sentinel-2 optical data. And the reason that we have to do that is because icebergs can become, they have a lot of motion, so they can basically drift. And so we have to get those optical images taken at around near or around the same time as the radar images. Yes, the region we're looking here is the Franz Josef region in the Arctic. Yeah, so to kind of carry on from what I was saying, so the reason that we're doing this is fast ice is sea ice that is connected to the coastline and also towards the seabed. And when icebergs become embedded within those sea ice flows, those fast ice flows, they stay there. And that means that we know that if we can validate them in the optical images, they're there. We can then use the same synthetic aperture radar images for this deep learning approach that I'm going to tell you. Also, this landmask is very important for eliminating any land features when it comes to doing the labeling. Yeah, so these are the images on the left here that just show you that kind of how that works. This synthetic aperture radar image on the left and the optical one, the middle, the landmask on the right. So what is the problem that we are trying to solve? You can't easily separate icebergs from sea ice, as I said, due to that backscatter signature. So we need an algorithm of some kind to do a little bit of discrimination. The solution that I'm suggesting is this right here. It is basically a dual polarization intensity ratio detector. What it does is it takes a SAR image and it performs what you can kind of think of as a blurring effect. It does spatial averaging of two different polarization channels in the image, and then when that blurring occurs, we need to then gain information about the intensity back. So we do the cross-polarized multiplication that you can see on the right here, and that gives us images that show us icebergs in a much easier way. That T on the right is a threshold, so we apply a different threshold, we get something out, we get an output. So yeah, we can utilize that cross-polarized HV term, where it is shown in the research that icebergs have a very strong signature in cross-polarized images. But after we have that image, we still need to quantify it. Now we could do it the old-fashioned way that I've been doing in my PhD, where we use receiver operating characteristic curves with or without a constant false alarm rate, CFAR. We do that to find the most optimal performance, basically. So that's what I've been doing in the past with lots of different detectors there on the right. The issue with this one, it requires a probability density function. It requires a statistical model of each different detector and each different threshold, and it would take a long time. It would be very complex. For real-world detection and for operational purposes, we need something that's more automated and takes a little less time, is more efficient. This is where this deep learning approach comes in with computer vision, and we can use this to identify icebergs by drawing bounding boxes around the objects. So in the past, we've actually tried this with faster RCNN. The problem that we had is that it was simply the machine we were using was a little outdated, so we had to expand upon this a little more efficiently using this YOLO V8 model. Basically, it does a forward pass, does only one forward pass basically in a region. So the methodology of this is basically we take a SAR image, input it, we calibrate it, in polarimetry we produce a covariance matrix of each different pixel in the image. Then we filter it out. We filter out the speckle noise that are very common in radar images. We create the labels of the icebergs. We have to do that laboriously. It does take a long time. We have to visually inspect each image ourselves manually. We have to decide, okay, is this an iceberg? This is an iceberg. This is sea ice, etc., etc. So we have to do that part manually. And that is a major limitation that we have in the research right now, is a manually labeled iceberg data set. It takes time. So we apply that landmask, and then we do the training and testing of the model. And then all the other bits come afterward as well, if we want to tweak it and get it a little bit higher in accuracy. So yeah, that's basically what this process is showing here. You've got the HH image and the HV image there, the cross-polarized on the right, the co-polarized on the left. We apply this algorithm that I talked to you about, and we get something out of it. These are what the images on the right, bottom right here, are showing, the input here. These are what we're going to feed into the model. So this is the raw data that we have to produce before we can even start training the model. And this is basically what happens. We perform a convolution. We put that filter through on the image, and because the image is so large and we want to reduce computational load and computational size, we're doing subsets of each image, so we get 400 image slices out of this. So this is what this animation is showing you here. It's basically called a sliding window technique. But you can perform it with a convolutional neural network as well. So it's basically the idea of convolution is putting a filter over the SAR image, and you get something out. And again, yeah, here again, the top images are the ones that I have produced, and the bottom ones, oh no, sorry, these are the ones that I have produced all along. There are examples that I will show you later that were from the previous work as well. You can definitely see the brightness on the bottom. These are the SAR images, where we've applied that filter and that land mask to make sure that those icebergs are actually there. And then we validate it with the optical images above. Here we go, yeah. So the top images here are the ones that I produced. These are where the ground truth and the predictions are basically, I'm showing you a qualitative assessment. I'm showing you like 1 or 2 image assessments here. And the bottom images are from the previous work that was done in the astrophysics lab that we have at Lancaster. And they had some kind of similar results too. But yeah, the blue squares here and the red squares show the ground truth and the actual predictions of the bounding boxes. We then need to quantify that performance with evaluation metrics such as the precision recall and the F1 score, very common in all machine learning and deep learning applications. But basically, for our purpose, we want the performance to be in the top right corner as much as possible. Basically, each F1 score, precision and recall, represents a threshold of confidence in the objects if they are icebergs or not. So here are the initial results of the training. Initial results suggest no overfitting. We only really trained this for 50 epochs because our data set is a little limited. We need more data in the future to be able to get a better training result. But for now, we have a precision of 0.8 with a recall of around 0.8. And this is to be expected with SAR images, the resolution issue, of course, what I told you about, the backscattering issues, etc. But the aim is to find the highest precision and the recall. Again, that top right corner is really important. So the conclusions that I can give you are basically, given that there is increased shipping in the poles and the increased presence of icebergs, we have a need for this additional safety feature, this detection system that I have been working for the last 2 years to design. Our AI-powered system does appear to work well initially, but the next step is to tweak it further, kind of develop it in terms of the speed, the generality, and the ultimate goal is to test it in a live situation. So take it to stakeholders and basically tell them, okay, these are the results that we have. We can send you coordinates and locations of these icebergs twice a day, depending on the Sentinel-1 acquisitional time. But we're currently having conversations about this. So that's pretty much it. Thank you very much for listening. If you have any questions, please come talk to me.
Great, thank you, Sonny. Any questions for Sonny in the audience? Yeah, at the back there.
Hi, yeah, I have like 2 questions. The first is have you thought about testing a quantized version of your YOLO model and what the performance difference would be? Because then you can maybe deploy it on board satellite. And then the second question is, how much notice do you need in a live scenario? Because I'm just thinking about the acquisition schedules of Sentinel-1. I think they're 12 minutes.
Yeah. Can you repeat the first question again? I'm so sorry.
Have you thought about testing a quantized version of your
Quantized. Sorry.
So you can reduce the model size and then
so that is something that we are considering. So the YOLO V8 does have different architecture sizes as far as I'm aware. So it goes from small, medium, large, very large. We tested this on a large. We were thinking if we had problems with the overfitting or limitations there, we could try it on a small and then see if we can go from there. But for your second question, sorry, I've lost my train of thought. Can you say the second question again?
For live testing,
testing.
how far ahead do you need?
So for a live testing, we haven't really done it properly yet, but we are thinking that we need to get Sentinel-1 images of the locations. I would say in the rough 1 to 2 days, and where we can then kind of gauge what's happening with the drifting area as well. If there is an iceberg in the general proximity that we can give to those ships that are about to cross those areas, I would say 1 to 2 days ballpark.
Yes, sir.
Could you provide an intuitive explanation of the intensity ratio that you were using? Because in the numerator you had the HV channel, which is an indication of the volume scattering in SAR.
Yeah.
And in the denominator you had the HH channel, which is an indication of the surface scattering. So how come the ratio would provide information about the iceberg? This is something that
Yeah, so icebergs show a very strong volume and surface scattering in SAR images, as because you have a lot of undulations and a lot of cracks within the iceberg body itself. So it's not like ice that you find in your glass of water, for example. There's a lot of natural variation there, and that can cause a lot of the volume scattering to appear quite proximal to the iceberg. So I would say that volume scattering is one of the biggest elements, but we also do have that surface element as well. Icebergs can topple over, it can rain, it can get sea spray, that can affect dielectric constant and cause things to do, cause the surface scattering also to change. So again, that threshold that we set for the ID pole ride is, that detector is important. Does that answer the question?
and should this be HV in this equation or VH? So the other slide that you had, it was HV. I see that because in Antarctic and Arctic the polarization are HV, not VH, right?
Yeah, so that's a good point actually. That one there is the dipole rad, and the other one is the dipole rad, which uses a different polarization. I just got to tweak that one. But thanks for pointing that one out.
Okay, thanks for the questions. Maybe some of that can be followed up in discussion afterwards. Let's thank Sonny again.